So in continuation with the previous lecture where I started with the filters and defined frequency as a frequency selective electrical circuit which passes a particular band of frequencies and rejects another band of frequencies. Now our focus is on those type of filters where you have, this is a rectifier and this is a load RL. I am interested that here I should get a pure DC and I am getting a pulsating DC here at this stage. So what I do, I simply apply a filter here. This is a filter which will pass the low frequency component. This comprises of both AC and DC. You can say it has low frequency as well as high frequency component in it. We are interested in this low frequency component. It means it should pass low frequencies and it should stop the high frequency components here. This is the main kind of filter that we are interested in, and these filters are called low pass filters. Our focus here is on the low pass filter, although there are various kinds of filters are there. High pass filters are there, band pass filters are there, band stop, band reject, various types of filters are here, but our interest is on these low pass filters. Okay, so as I said that these filters are the frequency selective elements, and the main components which are the building blocks of any filter are two things. It is capacitor and an inductor. Without this you cannot have a filter. Alright, it can be either made by the capacitor or by an inductor or a combination of capacitor and inductor. Now see, look at the basic principle of working of a filter. What happens, see this, look at this capacitor. You must have come across this word Xc, that is called the capacitive reactance. It is given by 1 upon 2 pi Fc if F is the applied frequency. Alright, or if F is the frequency of any signal, if F is the frequency of the signal. Alright, so this Xc is given by this much. Now what will be the value of this Xc? Xc is nothing, it is, we can say that it is a kind of resistance offered by this capacitor for a particular frequency. So what is the value of this Xc for a DC? DC means this frequency will be 0. Alright, it means that the value of capacitive reactance Xc for this will be infinite. It means a capacitor offers infinite resistance to a DC. Alright, you must have come across this word that a capacitor passes AC. Means it passes the high frequency component as it is offering infinite resistance to a pure DC, or we can say that as frequency increases this decreases. And another thing, look at this L inductor here. Okay, in this inductor you must have come across this word XL, inductive reactance. It is given by 2 pi FL or omega L. This 2 pi F is also represented as omega. Now again, this is nothing but simply a kind of resistance offered by this inductor to a signal of frequency F. Now for DC, what will the value of this XL for a DC component? For DC component means pure DC, this factor is 0. So value of XL will be how much? It is 0. Means it offers 0 resistance to a pure DC. It passes the DC. Is this clear? This is the basic principle of any filter. Alright, this is the basic principle of any filter. And remember that one more thing, when we talk about, our focus is on low pass filters. Alright, our focus is on low pass filter. So this capacitor is always applied in the shunt arm or in the vertical arm. On the other hand, this inductor is always applied in a low pass filter in the series arm or in the horizontal arm. What do I mean by this? See, suppose you have an electrical circuit like this. Suppose this is an electrical circuit here. An electrical circuit like this. These arms, these are called the series arm or the horizontal arms, and these are called the shunt arms or the vertical arms. So capacitor is always applied in a shunt arm, and this is applied in a series arm. Alright, now let's come to different kind of filters. Let's start from here. These are the different kind of 4 types of filters that we have to study. This is called the shunt capacitor filter. Alright, if this is not here, it is a simple, this is a rectifier. It can be a half wave or a full wave rectifier, and there is a load here. Between this output of the rectifier and load, I have applied a capacitor which is acting as a filter. Now what happens? Here you have both AC and DC. This AC will be bypassed by this, and here you will get a comparatively better DC, not a pure DC, and it will improve the ripple factor. I told you the main function of the filter is to improve the ripple factor. The ripple factor of this for a full wave rectifier, if this rectifier is a full wave rectifier, is given by 1 upon 4 root 3 F into C into load resistance RL. Okay, and for a half wave rectifier, if this is a half wave rectifier, naturally it will be high, so it is given by 1 upon 2 root 3 FCRL. Okay, next comes the inductor filter. This L is applied in the series arm. Okay, now what will happen? Again, here it will have AC as well as it is a DC component. This DC will be passed by this and it will block the AC component. Okay, and the ripple factor for this is given by, for a full wave, I'll start with the full wave rectifier. For full wave, the ripple factor is given by this RL upon 3 root 2 into omega. Omega is the angular frequency of the signal here. Alright, 2 pi f into L. See, this is L is a suffix and this is the value of this inductor L. Okay, and for a half wave rectifier, this is given by I'll write directly here, 1.13 RL upon omega L. Direct. Then LC filter. This is called the L section filter. This filter is also called the L section filter. This is called shunt capacitor. This is called series inductor filter. This is called L section. If you look, it is in the shape of a opposite L, and the ripple factor for this is given by, see what will happen. This here you have both AC and DC. It will pass DC, block AC. If some amount of AC is left, it will be bypassed by this capacitor here, and at the output you will get comparatively better DC as compared to these two. Okay, and this is given by, for this one, for a full wave, of course, it is given by gamma is 1 upon 6 root 2 omega square LC. And last, this filter is called the pi section filter. It is called a pi section filter. If you see this one, this portion is looking like the pi. Okay, it is also called CLC filter also. And now what will happen here also? If you look at the basic principle, here you have both AC and DC. AC will be bypassed by this. It passes AC and blocks DC. Now it is blocking DC. So this DC will be passed by this. It will always follow the minimum resistance path. Okay, if any AC is left, it will bypass by this and you will get a comparatively better DC in this case. Okay, so the ripple factor for this is given by root 2 upon 8 omega cube. Omega is 2 pi f. What is the frequency of this signal? C1 C2 L into RL. As far as the derivation of these ripple factors are concerned, they are not part of your syllabus because they require Fourier series. Alright, if you need it, I'll provide the literature this for you. Okay, so for the time being, I'll stop it at this point.